Hi, this is Miss McBride, and we're going to be covering a very important section today in 4.3, discussing measures of variation. So our goal is to understand and therefore be able to interpret, find, and use common measures of variation. We're going to look at the range, the 5-number summary, and the one that's most often used called standard deviation. You will need your graphing calculator, your TI-83 or 4, so please have that available because I'll have you entering data so you can come up with the same solutions that your PowerPoint author does, but they're using the hard formulas. I want you to just do it in your graphing calculator. All right, so why does variation matter to start with? So let's just start by looking at an example. So you've got customers at the big bank can enter any one of 3 different lines leading to 3 different tellers. Best Bank, a different bank, also has 3 tellers, but all the customers wait in one line and then are called to the next available teller. Now you've done this before. I personally know I like the way Best Bank does it. I want to get in one line, and then as somebody comes open, I don't have to guess if I picked the right line or not. So here are some samples of wait time, and they are arranged in ascending order. All right, so we got our big bank going from 4.1 up to 11, and our best bank going from 6.6 up to 7.8. So you'll probably find more unhappy customers at the big bank than at the best bank, but this is not because the average wait's any longer. In fact, the mean and median wait times are 7.2 minutes at both banks. So the difference in customer satisfaction comes from this measurement called variation, the variation at the 2 banks, which can be described as the spread of the data. So even though my mean and median are the same, that doesn't tell me how the data values are clustered about that mean or median, how far the spread goes. So if we took a quick look at a histogram here, my waiting time for the big bank is on the left, and my waiting time for my best bank is over on the right. And show how we have our binned data. So the waiting time for the big bank is more spread out. It has a bigger variation than the small bank, where everybody is clustered about the same number because they're consistently just getting called to the next teller. All right. So why big bank with 3 separate lines should have a greater variation in times? So consider the several places where you commonly wait. Do they use a single customer line that feeds or multiple lines? And I already gave my opinion on this. I like the one big one that feeds, because if you happen to get into the wrong line, which could explain why you have a bigger variation on big bank, you got a really short, somebody who goes fast, and then you got the teller who goes super slow, and these customers just end up waiting and waiting and waiting because the person who has 6 things to do, as opposed to if they just got called to the next teller, you can kind of work around that one person who's taking a really long time. All right, so let's talk about some measures of variation. The first and the easiest is called the range. The range is a set of data values. It's just the difference between the highest and the lowest. So the highest value is going to be called our maximum, and the lowest is called the minimum on the graphing calculator, so I want you to get used to those names. So the range is just going to be the max minus the min, the highest value minus the lowest value. All right, so now this can be misleading, so let's take a look at the 2 sets of quiz scores for these 9 students. So which set has the greater range? And would you also say this set has the greater variation? All right, so let's take a look at this. My range is my max minus my min. So for quiz 1, it would just be 10 minus 1, or a range of 9. For my quiz 2, it would be 10 minus 2 for a range of 8. But you can see that even though quiz 1 has a bigger range, it has a smaller variation because most of the scores were a 10. The other one has a smaller range, but the grades vary much more widely. So a single score, an outlier, has no variation because those other students all got a 10. So I have to be a little bit careful here. Now, no 2 students got the same score on quiz 2, so they're spread out a little bit higher. So we'll look at some other ways to measure variation, because again, range is very crude. It just tells me high from low, and it doesn't really give me a good idea of how each individual value is spread about the mean. All right, so another way to look at variation is looking at a box and whisker plot. So here we use the idea of position that marks a data value's position within an ordered set of data. Ordered set of data means I'm going to put it in ascending or descending order. Usually you do ascending, so we'll start with our low and go up to our high. And we're going to look at the positions as we go along to see how far apart in quartiles every fourth position. So quartiles are values that divide the ordered data distribution into quarters by position. Now remember, if you want to get 4 pieces, like you take a box, you only cut it 3 times because each of those cuts it into 2 pieces, so 3 cuts gives you actually 4 sections. So our lowest section is the lower quartile. Q1 is actually that number, 5.6, that separates the lowest fourth. So 4.1, 5.2, 5.6 are my lowest fourth. Then I got 6.2, 6.7, 7.2. 7.2 is your middle number. Your 3/4 of the way through, or quarter 3, Q3, is 8.5, and then my maximum number is 11. So be careful here. Q1, the lower quartile, is a number. It's an individual number that cuts the data into these fourths. The median, Q2, is the number that cuts the data into halves. Q3 is one piece of data that cuts it at the 3/4. So I've got 1/4 above and 3/4 below. So the Q1, Q2, Q3 are individual numbers that cut the data into the fourths. All right, so here we're going to take a look at these quartiles, Q1, Q3, and we're going to define them as such. So that lower quartile, or Q1, divides the lowest fourth from the upper 3/4. It is the median of the data in the lower half. That's one of the ways you explain it. So you exclude the middle value, remember, if it's odd. All right, so the middle quartile, or the second quartile, is the overall median of the data, because again, it cuts all the data in half. The upper quartile, or Q3, divides the lower 3/4 from the upper. So it's the median of the upper half. So if you were going to be finding these longhand, you would be working that, but we're going to do it right in our graphing calculator. And I love these technical notes. Statisticians don't always agree on everything, so they don't have a universal procedure. So we're just going to use the method of our graphing calculator because you can get slightly different results. All right, so now what we're going to do with these quartiles is we're going to put them together with the max and the min and get this thing called a 5-number summary. This is the data distribution, goes from my low up through my high, and then cuts the data into fourths. So on your graphing calculator, the low value, you'll see it called the min, the lower quartile number Q1, the median is called Q2, or upper quartile Q3, and that high value we'll say max. So here they give us the 5-number summary for the big bank and the best bank. So notice they have the same median, and the other thing to notice is there's no mean on this. This is all about position. Mean is an average, it's not a position. So median is a position, it's in the middle of the data, as are the low value, the min, Q1, Q2, Q3, and your max. All right, so that's your 5-number summary for each bank. Now we're going to make this thing called a box and whisker plot. What I like to do is get the 5-number summary on my graphing calculator, and then I draw it by hand. Getting it on the graphing calculator is longer. Sometimes it's just harder. It's longer than just doing it by hand. So the first thing we do is draw and uniformly scale. I can't emphasize that enough. You need a uniform scale. So look here. See how I go from 0 to 12? I've got a tick mark every one. If I counted this not uniform scale, then I wouldn't get the proper proportions. So uniform just means you're counting by the same number. Let's say I counted by 2s, I'd have 2, 4, 6, 8, 10, 12. So you just have to be uniform spacing. All right, once you've got that, you enclose the values from the lower quartile Q1 to the upper quartile Q3 in a box. So what I usually do is just draw a vertical line at Q1, Q2, Q3, and I make a box, and then I already have the vertical line through the box at the median. So I just do my 3 vertical lines all at once. Q1, Q2, Q3, draw the box. That's the box part of, sometimes this is called a box and whisker plot. Then we add what are called the whiskers that go from Q3 out to the max and then Q1 back to the min. So this now shows my spread of data by force. So I know that the lower 25% for the big bank is between 4.1 and 5.6. The middle fourth is 5.6 to 7.2. The third fourth is from 7.2 to 8.5, and the highest fourth is up from 8.5 to 11. Now look at the best bank. See how the median is the same, but it has much less variation. It's much more tightly clustered around that median. So hence, my variation is much smaller for the best bank. So if you went into that bank as a customer, you knew you would consistently get out between 6.5 and 7.5 minutes. If you go into the big bank, you could get out really fast, or you could be there over 10 minutes, a decent amount of the time. All right, so that's a box and whisker plots. It's a nice way to show variation about the median. All right, the box plots shown in this book, are called skeletal box plots. Sometimes they make them slightly differently. I always do the little whiskers with the lines, or you could do an asterisk. Sometimes they look a little different. Oh, all right, let's take a look at percentiles. Here you've seen percentiles before. If you took the SATs, you were told you were in the 70th percentile. And if you never were sure what that meant, that means I took the data set, in this case all the people you took the SAT with, and they were chopped into 100 pieces using 99 lines. Because remember, I always use one less line than I do how many boxes I want. I want 100 pieces, so I'm going to draw 99 lines. The data set divides the bottom n percent from the top n percent. So a data value that lies between two percentiles is often said to lie in the lower percentile. You can find the value of a percentile by using the following formula. You'll take the number of data values, and here's the key thing, less than the data value of interest, and divide it by the total number of values in the data set. That'll give you a decimal, and then you multiply it by 100 to convert it to a percent. So just as an example, like I said, if you had scored in the 70th percentile on the SATs, that means you did better than, in other words, 69% were less than you. And if you were in the 90th percentile, that means you did better than 90% of the people. It does not mean you got a good grade on the SATs. You could have everybody do terribly on it, but if you beat out 98% of those really bad people, you're still in the 98th percentile. So this is by position again, and it has to do with what's called your cohort, how well you do on a particular day. If you happen to go and take your SATs on the day when all the geniuses are there, you may score a lot lower than if you went on the day where low scoring people went. So it's all about who's in the data set with you as to whether you're in the top or bottom percentile. Again, it's not how much you passed a test with, it's compared to the other people, how many of them did you beat out. All right, so to find the data value corresponding to a given percentile, we can multiply the number of the data values by the percent and then count. So for example, if I have 50 sample values, the 12th percentile would be found by multiplying the percent, 0.12, times how many were in my sample of 50. So the 12th percentile would be the 6th value. So I would have to number my values and then just count out 1, 2, 3, 4, 5, 6. And this 6th one is the 12th percentile, which means that person did better than 12% of the people. All right, so we need to find 104.54. So you keep looking, and 104.54 is the 35th person on the smokers. Once I know that, I do one less than that, which would be the 34th person. So the number of values less than that 104.54 was 34 because it itself was the 35th. We had 50 values, so that's what I divide. 34 divided by 50, multiply that by 100, and you'll get 68. The decimal would be 0.68. So that means the 35th data value, the value 104.54, marks the 68th percentile. They were higher than 68% of the folks, or the 68th percentile. That number had 67 below it. What is the percentile for a data value of 61.33 for the non-smokers? So you'd go back to the table, look up that number, and you would find that it was the 50th. It was the highest. So I have to do the number less than that then would be 49 divided by my 50. So that data value of 61.33 marks the 98th percentile. That means you have more than 98% of the other people. What data value marks the 36th percentile? So here we're working backwards. I'm giving you the percentile for the smokers and then the non-smokers. So if I know the percentile, I will multiply it by the data set and then count up. So we'll multiply the data values. I have 50 times that percent, 0.36, and then count. So we have to just count up. 50 times 0.36 is 18. So I'm going to count up on my table to get to the 18th value. For the smokers, this is 20.16, and for the non-smokers, it's 0.33. Now we're going to take a look at standard deviation. This is one of the most important measures we have for a data set, and we're going to be using this a lot as we move into our later information about inferences. We're going to be using means and standard deviations to make lots of inferences about data sets. So this is a real critical one. Statisticians often prefer to describe variations with a single number. The most commonly used to describe a variation, used in tons and tons of formulas, is the standard deviation. It gets the name standard because it's very typical. How to calculate the standard deviation? Here's what I say. I use the, oh gosh, it should be TI-8384. There's a typo. And not the formula. But sometimes people like to see the formula. It's quite complex, so I want to go through it. But just know when I ask you to find the standard deviation, I expect you to pull out your calculator and follow the steps I'll show you here. And it's also on that little video on Chapter 4. If you go click into the folder, it says little video. It shows you how to find the mean, the median, standard deviation, and the 5-number summary. It's all in the same quick command. You just have to know how to work it. Now, if I want to do it the long way, first I need the mean. Then for every data value, I have to do the data value minus the mean. Then I find the squares of all the deviations from the mean. I add up all those squares. Then I divide this sum by the total number of data values minus 1. I always do the minus 1 because it's a sample and I lose what's called 1 degree of freedom, and we'll talk more about that a little bit later. So basically, these steps produce the standard deviation formula. Now remember, standard deviation is going to tell me how far a data value varies from the mean. That's why I subtract from the mean. I'm trying to get a standard number that tells me how far I am from the mean. Now I move the slide up. It'll be here in a second. Now this technical note is very important. In finding the standard deviation, when dealing with data from a sample, one part involves dividing the sum by the number of data values minus 1. When you deal with an entire population, the formula is slightly different. You do not subtract the 1. but for the purposes of this book, we are going to use only the formula for the sample to find S. And I'll talk in a minute. S is your variable for the sample standard deviation. That's what we're going to be finding in this book. Now, if I take the result of the standard deviation and square it, that thing is called the variance. It's used in advanced stuff, but again, we're not going to use it in this book. But sometimes people like that. Let's calculate the standard deviation then for the waiting times at the big bank. If you're going to use the formula, here's what you'd do. You'd start with the first column and you'd find the mean. Once you had the mean, which was 7.2, notice you subtract it from each individual data value, which gives you positives or negatives. So to take care of that, we square it. That just gets rid of any negative values because we don't want to deal with those. Then we add those all up. You'll get that 38.46 at the bottom. Then we divide by the total number of data values minus 1. We had 11, so we divide by 10, and we get 3.846. Then I square root that to get 1.96 minutes. Here's the formula. It's a great little formula, if you like formulas, but we have this delightful graphing calculator, so I just like you to see the formula to see what we're doing. I want you to also make note of the variable S. Standard deviation means actually sample standard deviation, not population standard deviation. It is my conventional symbol, so write that down. We now have N for sample size, we have X bar for mean of a sample, we have S for the standard deviation of a sample. Tells me how, the sample standard deviation tells me how far my data varies around the mean. If I was going to be using the population standard deviation, I would use this letter called sigma. Now, let's take a look at this same problem using your TI 8384. So, have it out. Remember how to go to list 1. We talked about that back in section 4.1. You go to stat and then edit, and in L1 you'll put your 4.1, 5.2, etc. So pause the narration if you need to do that. Once you get those all in, always remember to quit to go to the home screen. Then from there enter stat calc, one variable statistics, and put in L1, either in parentheses or in the little box, depending on what year your calculator was made. Now look for the symbol, it's several down, called SX. That's your sample standard deviation, and you should see 1.9611. Now here they rounded to the nearest hundredth, so if we did that, we would exactly get the same value they did using the formula and a whole lot faster. So if you're having trouble getting that number, go watch the video on Blackboard that tells you, I actually show you with a calculator how to get those values in and work the standard deviation. Now, how do I interpret it? A good way to develop a deeper understanding here is to use this kind of a down and dirty range rule of thumb. It's less accurate, but it's easier to calculate quickly and gives us an idea of what the standard deviation does for us. This range rule of thumb uses the range, and I cut the range into fourths, 1/4, by dividing it by 4. So notice the little wiggly equals are approximately equal to. So this is just a real down and dirty approximation, and it does have some limitations. But basically, if you took your data and divided it by 4, the range of it, you would get a number fairly close to the actual standard deviation, and it's much easier to think about. So the range, remember, was your high minus your low, or your max minus your min, and then divided by 4. Let's find the estimated standard deviation for the waiting time at the big bank then, and compare it to the actual value we found in the example. So my range went from 4.1 to 11, so my range is 6.9 minutes. If I divide that by 4, take a fourth of it, that's 1.7, and the actual standard deviation was 1.96. So those are pretty close. Puts us in the ballpark. So it can be useful. Now, what if we know the standard deviation? We can also use this to estimate the high and the low values. So the low value is we start at the mean, because that's my center. Well, that's the median, but it's my central value. And I'm going to subtract 2 of those standard deviations. To get the high value, I'll start at the mean and I'll add 2 standard deviations. Now, make note that this doesn't work well when I have outliers, because you're not going to get way up to any big outliers using this, because remember, it's just a rough rule of thumb. So if you see huge outliers, you would not want to use this, but if you have a fairly symmetric graph, this is a good estimate of the high and the low given the mean and the standard deviation. So if you've got gas mileage for your BMW varying under different conditions, it gets a mean of 22 miles per gallon and a standard deviation of 3 miles per gallon. So I'm just estimating the min and the max of the typical gas mileages that I could expect under these driving conditions. So to find my low value, I'll do my mean and I'll subtract 2 standard deviations. So 22 minus, you can do 22 minus 3 minus another 3 to get 16, or you can do 2 times 3 to get 6 and then subtract to get 16. Your high value, start with that same mean of 22 and then add 2 standard deviations. So you can do 22 plus 3 to get 28, or do the 2 times 3 to get 6 and add that to 22 to get 28. This tells me that my lowest value is approximately 16 miles per gallon and my highest was approximately 28, given my 22 miles per gallon as the mean and a standard deviation of 3. Again, you don't need this formula, just kind of interesting. It's the square of the last one, because the relationship between variance and standard deviation is one is the square root of the other. All right, let's look at some examples. Now, I put the answers here for you so it was easier to see, but I do want to talk them through. So in your graphing calculator, go ahead, to find the range, we're just going to find the high and the low and subtract them, but sometimes I've been known to pick the wrong high and low. So what I would have you do is go ahead and pause this and put those numbers into L1. Once you've got them in L1, then do your stat, calculate one variable statistics. And once you've got that, now you can find your mean. You can find your SX. You should see the result is 105.9. Number 10 under the, where it says space shuttle flights and gives you the data, right under there is the answer. So the range would be your high minus your low. So when you're looking at your 5-number summary, you should see min is 0, max is 381, so your range is 381. They tell you how to do it in Excel. I just have you do it on your graphing calculator. So the standard deviation, SX, should be 105.9. So go ahead and give that a try. Once you finish that one, go to the one over to the right, the Old Faithful geyser. So go back to L1 and remember to clear it out. You can go up arrow, it'll highlight L1, then hit clear, which is below the down arrow. Don't hit delete, hit clear. Down it will come down and hit enter and it'll clear it. Put in your new data, do your stat, calculate one variable statistics, find your 5-number summary to get the range. You should see the low is 65, the high is 98. So if you subtract those, your range should be 33. So the graphing calculator gives you the high and the low. You have to do the subtraction to get the range. It will immediately give you the standard deviation. You should see by the SX, it should be 8.9. Now, another interesting thing to take a look at, BMI is body mass index. They're looking at the body mass index for Miss America. The trend of thinner Miss America winners has generated changes that the contest encourages unhealthy diet habits among young women. They're trying to keep their weight lower than is healthy. So listed below, here's a study of that, is the body mass index for Miss America winners from 2 different time periods. We're interested to compare these does there appear to be a difference in variation? So from the 1920s and 30s, here's the BMI, body mass index. So go ahead and put that first set into L1, find your mean and your range and your standard deviation. Write that down. Now if you want to put the second set in L2 and not erase the first set, this is a good chance to do that. So from the recent winners, go Stat, Edit, and L2. Put this data. Don't erase the L1. Put the L2. Then when you go back to your home screen, you do Stat, Calculate, and put L2 in the parentheses or in the box and enter. That way you've got both pieces of information there and you haven't erased the old one. So from the earlier data from the 1920s and 1930s, hit pause while you work this all out and then come back to check it. You should have found your range had a high of 22.3 to a low of 18.4. So your range for the earlier contestants was 3.90 and their SX, standard deviation, was 1.48. I found it on the graphing calculator. So for the more recent data, your range is 20.3 minus 16.8 or 3.5. So there is a smaller range, but the standard deviation is 1.19. So there's actually less variation in the more recent BMI than in the older from the 1920s and 30s. So if I put that together with the fact that the mean BMI is also decreased, it appears that the contest winners are expected to conform to a thinner body type now than they did years ago. So that's a nice way of comparing two distributions. And if you wanted to, you could make a box and whisker plot of each of those to take a look at that as well to see where the median and the variation comes from. All right, let's see, we did Old Faithful. All right, calculating our percentiles. So remember, to calculate a percentile, you'd find the value that's one less than the one you're interested in and then divide it by the total number. So here we have a data set of 85 ages of women at the time they won that Oscar for Best Actress. So part A, one of the actresses was 40 years of age and she was older than 63 of the other actresses at the time that they won. What is the percentile of the age of 40? So what I'll do is, I know she was older than 63 of the others, so I've already subtracted my 1. So I do 63 divided by how many we had, were 85, times 100, so you can see the answer underneath. The percentile then would be 74%. So in the 74th percentile. You can look at part B and part C on your own if you want to pause, and then you can check the answers at the bottom. All right, let's take a look at comparing the variations. I picked out problem 26, but we're supposed to do these 5 things for it. The answer is over to the right because I did want you to see those box and whisker plots. So first off, we were supposed to find the mean, median, and range for each of the 2 data sets. So below, the data set for 26 gives the driving speed in miles per hour, the first 9 cars to pass through a school zone, and the first 9 cars to pass through a downtown intersection. So we're looking at their driving speeds. So the school, if you look over there, you can see its mean, median, and range, and the downtown, its mean, median, and range. All right, so that's pretty straightforward. You can again put 1 in L1, 1 in L2, and work those out and just jot down the numbers. They also wanted the 5-number summary, so write that down. And then I again draw my box and whiskers by hand, but I can't do this on the PowerPoint, so I cut and pasted the solution from the book there. So notice the uniform scale. My lowest of any of the data here was 18, yeah, and my highest was up in the 36, yeah. So I want a scale that incorporates all of those numbers. So this particular graph starts at 15 and goes up to 40 and counts by 5s. So I went 15, 20, 25, 30, 35, and then 40 would be up a little higher. Notice that could have as easily done from 14 to 36 and counted by twos, 14, 16, 18, 20. The key is to be uniform. Once you have the scale set up, draw your verticals at Q1, Q2, and Q3, and then connect those with the box, and then make your whiskers from Q3 out to the max and Q1 down to the min. And you can see that these box and whisker plots are extremely nice way to look at this, that the median speed is so much lower, obviously, in the school system. All right, so what else did they want to know? Find the standard deviation. All right, so part C says using Excel, but again, you can use your graphing calculator to find the standard deviation is 2.9 for the school zone and 3.9 for the downtown. So the values are more tightly clustered about the mean for the school zone than they are around downtown, which is good to hear. They're being more safe around the children. Part D says apply the range rule of thumb to estimate the standard deviation. So I'm going to subtract the range, subtract to get the range and divide by 4. And then I would get, the estimate would be about 2 for the schools and about 3 for the downtown. So the range rule estimates are reasonably close. Both are a little bit low to the actual standard deviations. But because I didn't have any big outliers, now how I can see that is look at those box and whiskers. If the whiskers are relatively the same size on each side, I don't have any real outliers. So I could say this was a good one to use for the range rule of thumb. Doesn't have any extreme outliers. Then last, based on all my results, compare and discuss the two data sets in terms of their center and their variation. So the speeds of the school zone average about 10 miles per hour lower than the downtown and have a little less variation, is what we could tell from that information. And the box and whisker nicely shows that. All right, last problem, 32. We got batting standard deviation. So over the last 100 years, the mean batting average in the major leagues has remained fairly constant, about .260. So they have around a fourth of the time they'll get a good hit. However, the standard deviation of batting averages has decreased from about .049 in the 1870s to 0.31 in the present. What that means is the data is spread more tightly around that mean of .26 if it has a smaller standard deviation. So what does this tell us about batting averages of players? Based on these facts, would you expect batting averages above .35 to be more or less common today than in the past? All right, so because their standard deviation is smaller today, that means we're tightly clustered about the .260. So a high batting average like .350 would be less common today because I have it more tightly clustered. We don't have any Babe Ruths knocking it out of the park all the time. I will not say more than that because I don't follow baseball that much. All right, but this idea of standard deviation is really critical to where we'll be going in future chapters. All right, you're ready to do your homework. Thanks. Bye-bye.